Welcome to week 5 on linear manifold learning. In this week we'll be discussing principal component analysis or PCA and independent component analysis or ICA. These are two techniques very broadly used across machine learning and data science domains. So the objectives for this week will be to first define what is meant by manifold learning and why it's commonly used. We'll then discuss the key differences between linear and nonlinear manifold learning, where the specifics on implementation of nonlinear manifold learning will be discussed in week 6. In the second video lecture, we will revise eigenvector decomposition in the context of linear transformations, which will be important for understanding the behaviour of PCA, and this will provide us with the tools that we'll need to derive PCA from scratch. On the other hand, ICA implementations are more complicated, so here we will focus only on understanding how to define statistical independence. And then we will learn how to apply PCA and ICA using scikit-learn, through which we will explore case studies where they are used for processing biomedical data. And by the end of this week, therefore, what we expect is that you'll know how to apply these methods, you'll know when to use them, and you'll know what their key advantages and disadvantages are. So let's get started with an overview of manifold learning, what it is and when to use it. Today's medical imaging datasets are very high dimensional. For example, let's take just one magnetic resonance brain volume. This is an image defined on a volumetric grid with a not unusual resolution of 255 by 255 by 180. So if we were to consider each data point as a separate feature, we'd have over 11 million features per image. However, MRI imaging is very expensive, so it's very unlikely that we would be able to acquire millions of MRI scans. This means that typically our datasets have many more features than examples. This is a problem because with increasing dimensions, the same amount of data fills the space more and more sparsely, leading to something known as the curse of dimensionality. So why is this so bad? Well, let's consider building a classifier of gender based on stereotypes, starting with something vaguely sensible, in this case height. In general, men are taller than women, so if we try and make a binary prediction on gender based on height, we are likely to do better than average. Thus, labelling gender based on who is taller or shorter than 170 centimetres classifies 5 out of 6 girls correctly, 3 out of 5 boys correctly, 8 out of 11 people correctly, and this gives us a 72.7% accuracy. So it does a reasonable job, but perhaps we can do better if we add more features. So what if we add a dimension on hair length? So this is now getting a little bit more unreliable. Nevertheless, in general, the girls in this sample do have longer hair, with some exceptions. So if we fit a decision plane as a function of height and hair, with all the samples found above the line labelled as girls and all the samples below the line as boys, we can do a slightly better job. With 4 out of 6 girls correctly classified and 5 out of 5 boys correctly classified, giving us an 82% accuracy. So we could stop there, but also perhaps if we kept asking questions, we could do better. What if we started getting really carried away by stereotypes and now ask about favourite film genres? So we might find that this specific sample fits our assumptions, with this top group preferring romance movies, the middle group enjoying comedies, and as it turns out, this lady down here happens to like horror movies. So this is great, right? We managed to classify everyone correctly. Well, no, actually, because in fact what's happened is we've heavily tailored our solution to our specific data points. We haven't increased the number of data points, so the more questions we ask, the more likely we will be able to get perfect separation just purely by chance. Well, sticking with the whole concept of stereotypes, let's assume that we next sample a biker and some goths who, of course, turn out to like horror movies, and next we have a Shoreditch hippie who likes romance movies, and some girls in the middle who, not unsurprisingly, like comedy movies. So now when we test our model accuracy, it's gone down to 61%. So in summary, if you have far more features in your model than you have samples, the curse of dimensionality can make it all too easy to overfit. Overfitting was introduced in week 2 as an explanation of what happens when you over-parameterize your model and give it too many degrees of freedom. This is exactly that. By giving the model too many features or parameters, it has too much freedom to fit to the noise in the data. So how can manifold learning help? In reality, datasets which reflect biological or physical processes are often constrained to a lower degree of freedom or dimensionality, which reflects the laws of physics under which they were generated. For example, think of the series of photos that goes into building up a panoramic scene. You might think that as these photos each have 16 megapixels, that it would be a very hard problem for a machine to figure out which points overlap. But actually, the process of taking these photos is embedded in 3 dimensions: the pitch, roll, and yaw of the camera. So in reality, the data points are embedded in a much lower dimensional space, greater than 3D due to the encoding changes in illuminations, etc., but far from 16 million. Another example of this is the process of trying to stitch together snapshots or MRI volumes taken at different time points during the breathing cycle. So in reality, all these data points can actually be encoded in simply 2 dimensions, where adjacent points on this simple 2D embedding represent the next volume in the temporal sequence. Famously, this process of demonstrating how lower dimensional data can be embedded in a higher dimensional space is often exemplified with the toy Swiss roll model. Here, hopefully you can see that this 2D plane has been rolled up into a 3-dimensional space. This gives a very clear example where the data is known to lie on an embedding in a higher dimensional space, and thus the convention of measuring Euclidean distances between data points is misrepresentative. As shown here, the Euclidean distance creates a shortcut between 2 distant points on the 2D manifold. Nonlinear manifold learning approaches therefore seek to recover the true low-dimensional space by ignoring Euclidean distances and instead considering local neighbourhoods. Before we get on to nonlinear manifold learning, however, we must address linear manifold learning. So what is the difference? What do I really mean when I refer to linear manifold learning methods? In essence, it's really quite simple. Linear methods are seeking to preserve Euclidean geometry by learning a linear subspace of the data. Nonlinear methods, on the other hand, break Euclidean geometry in a number of different ways. Most commonly, the idea they use is to instead seek to learn the local neighbourhoods of each data point. So in summary, modern healthcare datasets are extremely high-dimensional, often with many more features than examples. This is a problem because with increasing dimensions, the same amount of data fills the space more and more sparsely. And so this increases the possibility of finding a separating hyperplane by chance, and accordingly the chance of overfitting. Manifold learning techniques seek to avoid this by reducing the dimensionality of the data by learning a low-dimensional embedding. There are 2 broad categories of manifold learning techniques: linear manifold learning techniques such as principal component analysis and independent component analysis, which will be covered in this week, and nonlinear methods such as Laplacian eigenmaps, which will be covered in week 6. So this concludes this summary on the motivations behind manifold learning. Before going on to the next lecture, please complete the Keats quiz.